Okay, so hi, I'm Jed. I'm a student at Stanford University, and we're really proud of I'll be talking about a couple of papers here. The first one we came out with, it's a collection of students at Stanford, and then this latter one is some of the same students plus a postdoc who's now at University of Washington. And what I'll be talking about, I've given this cute little title, Friendship in the Axiverse. I hope that it's a nice end to this conference where I hope we've all made lots of friends, but also some pretty interesting theoretical physics that has some pretty direct implications for various kind of detection experiments, I think. Okay, so to start out with, let me just review a couple of things that you guys already know. So the axion, you've heard a lot about it at this conference already. I don't need to tell you more. Of course, the QCD axion was originally designed to solve the strong CP problem. The reason I'm talking about this here is because actually the axions I'm going to be talking today are generally not the QCD axion. They're some more general axion-like particles. Okay? These kind of particles are very generic in many UV completions of the standard model, many UV extensions of the standard model. So many types of string theory, you end up with a large collection of axions in the low energy theory. It's really interesting to understand these particles because that can be one of the few potential low energy signatures of something like string theory that's accessible to experiment. I won't say too much more about axion, like the UV origin of these guys, except to say that in general, when you look at the potential for an axion, you typically get something that looks like this. So there's some overall scale that sits out in front, and then the axions are typically angular fields, so that means that their potential is going to have some 2 pi rotational symmetry. Here I've given some heuristic, which is just a simple 1 minus cosine potential. The QCD axion has a slightly more complicated potential because it has actual QCD effects, but a lot of the UV axions that you might talk about arising will have potentials that look like this. The details aren't very important. The really important thing is just that qualitatively this is not a perfect harmonic potential. This is not just a mass term. Okay? The other thing I want to point out here is there are these two things that we generally talk about here. The axion's mass, you know very well what that is, and then the axion's decay constant, which I've written here as F. This decay constant plays a few roles in the theory generally, and one of those roles is that this is typically the scale that suppresses the axion's couplings to the standard model. We'll talk about that more later, but it will be relevant. For the QCD axion, this is just the QCD scale, but for some more general axion-like particle, these two things do not have to be related in any particular way. I'd like to remind you a little bit about some axion cosmology as well. There are many different production mechanisms for axions. The one that I'm going to be mainly talking about today is misalignment, where you have some axion, it starts in some potential, and if the symmetry is broken before inflation, then you can take the axion field to start uniformly across all space at some particular value. In absence of some better knowledge of what that value should be, you expect that that might be randomly drawn from something like its full field range, negative pi to pi. Of course, in more specific models, you might have shifts to this, but this is a pretty generic expectation. If you look in here, you'll see that that tells you that the initial energy density in this field is sort of on that scale, sort of this m squared f squared scale. Then you ask what happens to that. Well, we are physicists, we know what to do with the Lagrangian, we just take it, we compute its equations of motion. This field starts approximately homogeneously, so I can study the homogeneous component of this field and just look at how it behaves. What is that? Well, this is just a damped pendulum equation. Okay, so there's some friction, this is damping. There's also the fact that the term here, again, we're seeing that this is not a perfect quadratic, right? If I'm in the small angle regime, I can take sine theta is about theta, do your freshman physics thing, but if I'm not, this can actually matter, and we'll see that it does today. What happens as time goes on? Well, at early times when the Hubble rate is very large, this field is frozen. Once the Hubble rate decreases below the mass, it starts going through damped oscillations, and at late times, this is really just looking like a damped oscillating function. Okay? There's one harmonic in this field, it's just cosine of m, and then the rest is just some overall amplitude that's decreasing with time. Energy density goes as a cubed, where a is scale factor, so this is what tells you this behaves like matter. I'm belaboring these things because this will not be exactly the same with everything I talk about today. Now let me tell you why I didn't just say friendship for axions, I said friendship in the Axiverse. So what do I mean? I'm talking about a collection of axions that generically arises something like a stringy construction. These the potentials you can get are much more rich in structure, but at a first level, the kind of typical thing you get looks a lot like the thing we already had, just a bunch of copies of it. So we can have n axions, where n can be quite large. That's typically related to some topological numbers in the UV string theory. That can be order hundreds. You'll then also have many different contributions to this potential, each of which takes some similar form, except you can see that we can have sums over many different axions sitting in those in that cosine. So what this is telling you is that this is a bunch of oscillators, and they're actually coupled together. Okay, so that may already give you a hint that there might be some interesting dynamics going on. If we have any kind of remotely smooth spread in these, they're called instanton actions, then you end up with, over some large range, a roughly log flat distribution of mass. This is why people talk about axions, way down at 10 to the negative 22 eV, way up at 10 to the negative 3 eV. Like, you can really imagine that you have axions on many different mass ranges. And so with that background, I now want to pose the question, which I will then give you some concrete examples of really interesting physics happening. If we take this idea seriously, if we think that, our only, decent effort today at quantum gravity seems to be string theory, if we take seriously that and we try to imagine what the low energy spectrum might look like, we say there might be a lot of axions. Can we do something with that? Is it really just all the trivial dynamics we've already talked about, or do we get something interesting from having this rich structure in the theory? I hope I will convince you by the end of today that we do. So let's take a concrete example. That potential we looked at had n, where n could be hundreds, and the many different non-perturbative contributions to this potential. However, just from a basic understanding of oscillators, it should be clear that not all of those guys are going to be important for every single one, right? Oscillators generally talk to oscillators with relatively nearby frequencies. So that's what we're going to focus on. We're going to take a very concrete example of a pair of coupled axions that has a structure that looks like the one that we just wrote down. There are some phases and things that I've absorbed here, so you could have a phase factor in here, like a plus delta, phase factor in here, plus delta. Those can be absorbed by field redefinitions. I've written up here this in a way that looks very much like the potential I wrote a couple of slides ago. Down here, I've written the exact same potential where I've called these theta over f's. I've called these angular variables, so I've written them as thetas. Sorry, phi over f's, I've written them as thetas. And I've pulled out these overall scales into some overall mass and decay constant scale, and then some ratio of masses and decay constants. What I will tell you here is that you can get really interesting dynamics that emerge when you have some, like even a mild hierarchy in the decay constants and relatively nearby masses. So these aren't tuned to be incredibly close to each other. If you think you have hundreds of axions over many decades of axion mass, then just by coincidence you may have some that are within a factor of 2 of each other. So I will use the term short and long here in reference to their decay constant. So the short one is the guy with the small decay constant. The long one is the guy with the big decay constant. And we'll also see another nice analogy for these words. Okay, so what happens, and this is why we give it the name friendly, because these masses need to be somewhat close to each other. So let's first think about what these two guys would do if they were uncoupled. What happens? Well, each axion starts with a pretty similar, with an energy density that's like m squared f squared. Their masses are pretty similar, so the real relevant thing that's going to control this is going to be their decay constants. Here I have a decay constant ratio of 20, and so the long one starts with about 400 times as much energy density as the short one. When they enter the horizon, they do so at about the same time because their masses are about the same. And they just redshift down. So this dotted line is a cubed, and you can see that as time goes on, they just redshift down right like that. So the initial hierarchy is preserved all the way to late times. What happens with friendly axions, though? Well, these axions are a lot like coupled pendulums. Okay? The long axion has a much larger decay constant. If you work that out in the equations of motion, that corresponds also to something that's like a larger moment of inertia. So it really has the capability of driving the short axion. However, even a very basic understanding of freshman physics should tell you that you shouldn't expect that much to go on, because their masses are not super tuned close to each other, right? There's order 1 detuned from each other. What that means is, if you think about freshman physics, if you have coupled linear oscillators, you really need them to be sitting on resonance in order for any actual energy density to transfer between them, right? You'll have some beating pattern, sure, but in order to have actual energy density move from one end to the other, you need a resonance. And these guys are not on resonance. They're sort of only order 1 related in frequency. However, as I've said many times, these oscillators are not just linear oscillators, right? You really have something like a full cosine potential. And at early times, if you're drawing from a distribution that's sort of negative pi to pi, you're actually sampling somewhat large values of that potential at early times, potentially. If you have if you've ever pushed a kid on a swing, you know that like as you push the kid higher and higher, hopefully you don't push them this high, but as you push them higher and higher, eventually their frequency starts decreasing, right? They idle for a long time up here before swinging back around, okay? In the exact same way, the axion can adjust its amplitude to achieve resonance and stay there. This is a phenomenon in the study of nonlinear oscillators known as autoresonance. It's well known there. I think it's not as well known in our community. And a very concrete example of this is the exact same plot that I just showed you, but now with this effect happening. So where I've added the coupling back in, and you see that this guy is doing exactly what you thought at the beginning, but the short axion is just being driven by the long axion. It's adjusted its amplitude to sit on resonance, and then it tries to stay on resonance because it's constantly getting driven to just sit there. At late times, this has a really big effect. Now, in this plot, actually, most of your energy density is in the form of the short axion rather than the long axion, which is a dramatic reversal of your expectations. Here you see that these don't actually equilibrate. You actually get almost all in the short axion. The long axion falls off. Analytically, you can understand this. It's quite tractable. It's also very interesting. However, in the real world, once you take properly into account the fact that the fields are not perfectly homogeneous, that generally pushes you in the direction of equilibration. So I won't say too much more about that now. However, the main point is at the end, instead of having 400 times less of the short guy than the long guy, you'll have about the same amount of the short guy and the long guy. What dynamics are causing this? Well, it's really just the dynamics of a damped nonlinear oscillator. So I've drawn here a resonance curve. This blue guy is a resonance curve for a harmonic oscillator. Hopefully this looks very familiar to you. The damping here is coming from Hubble friction, remember? The pink curve is what's called a Landau curve. It's because Landau did a lot of work on this. It's the same resonance curve, but for a nonlinear pendulum. And so as you get to large amplitudes, the natural frequency of the oscillator actually shifts. And you can see that if you have a significant shift, there are actually multiple stable points that the axion can sit on. And the phenomenon I'm saying is basically that in some cases you get driven up to there. What are the key takeaways that I want you to get from this? I mean, there's a lot of really cool math. We showed in our paper. This is actually mostly analytically tractable, which is really cool. But for our purposes right now, I just want to say this is just the dynamics of coupled nonlinear oscillators, which is well understood. It can be quite generic, provided the two axions have somewhat similar mass. So this is not a rare thing. Of course, it depends on exactly what the initial conditions of the two axions are. Over here, I'm showing that. So as I'm scanning over the mass ratio, on the y-axis, I'm plotting the log of the density hierarchy. So anything below this horizontal line means the long axion is dominating. That's your naive expectation that would happen if they were uncoupled. Anything above this horizontal line is surprising. That's telling you the short axion has come to dominate. And what I've done here is I've just scanned over all possible initial conditions of the axion field. So I've just said, hey, I'm going to be a simple man. I'm going to say each axion is uniformly drawing from a distribution between negative pi and pi. And I find that in this kind of range, between 0.7 and 1, actually order 1 of the initial conditions end up with this reversed hierarchy. Okay? So this is not an uncommon thing to happen if you happen to have two axions like this. So there's a lot of really cool effects you get here. I'm not going to be able to go into all of them, but I do really want to talk about at least one of them, which is implications for direct detection, for a couple of reasons. One, because I think it's exciting for some of the experiments that you guys have talked about here, and two, because it might be the kind of thing that you would want to understand if you make an observation. So axions generically couple to the standard model, but they couple typically in a way that's suppressed by the decay constant. An example that you guys, all of you at this conference have seen before is like the axion-photon coupling, where this GA gamma gamma is typically suppressed by 1 over f. Haloscope experiments, if you're doing something like a direct detection experiment, so not for light shining through walls, something like that, but if you're building a haloscope, this is generally sensitive to the combination that's something like g squared times rho, okay, because you're looking for power deposited in your experiment. What does this look like for an uncoupled axion, just a lonely axion, one sitting out there all on its own? Well, as we said, the initial energy density in this field is actually controlled partly by this f as well. And so if you look at the present day abundance of an axion, you'll find that this depends on f squared, of course on the initial misalignment angle chosen, the mass. And then if you say let's compute this kind of figure of merit here, F drops out. Okay, so this is a point that I hope is not new to some of you, but it is a very interesting point, which is that if you have an Axiverse with many different axions, then if you think that they're being drawn from a distribution that's like, roughly uniform in angle, then the actual value of the decay constant doesn't matter so much for your direct detection experiment seeing it. It may be a very small subcomponent of the dark matter, but it will be coupled more strongly to the dark matter, or to the standard model, okay? What happens here, though? The short axion typically is coupled much more strongly to the standard model because it has a smaller decay constant. And so when it gets all of the long axion's energy density, you're kind of in this best of both worlds scenario. You've gotten the energy density from the guy with the big decay constant and the coupling from the guy with the small decay constant. The flip side of this is you might worry the long axion could be slightly harder to see. I don't have time to talk to you about the details here, but suffice to say that once you properly take inhomogeneities into account, it implies that energy densities actually roughly equipartition in most cases. This is a paper that we have out today, so you guys can go check the archive and look at it. Also, you may wonder, how do I confirm this? Well, I can go look for the long axion, right? I can try to resonantly scan over some narrow mass range right around the first signal you get. I want to emphasize again, this boost to visibility happens even if the friendly pair are only a subcomponent of dark matter. Okay, you do not need to be the dark matter for this to be more visible to you than another Axiverse signal. I have here a plot that I want to convey, and then this will be about the last thing I say. So what I've done here, I've plotted axion mass on the x-axis. I've plotted this figure of merit on the y-axis. I've taken a lot of help from Kieran's axion limits code, as have many people here. I think we're all in debt to him. What is plotted here, this blue line, is just the most naive misalignment line. So if you have a lonely axion that started with an initial misalignment angle of pi over 2, it would sit on this blue line. And again, I want to convey that the only thing that you should be thinking of as controlling where something sits here is that initial misalignment angle. What I've drawn up here in shaded blue, and the different colors and these dashed and dotted lines have slightly different assumptions on the model. I don't have time to get into it. But what I've drawn up here in shaded blue is the region of parameter space that you start covering when you talk about having perhaps a friendly pair in your theory. So the reason I think this is kind of important is, one, many of you who are far better experimentalists than I am, I touch things and they break, but many of you guys are building real experiments that are probing some of these regions up here. I like to think that whenever you build an experiment, even if it doesn't make it all the way down here, you think that it has a chance of discovering something. And I would say this is actually a realistic thing that it could have a chance of discovering. Another thing that's pretty important is, suppose you did discover something that sits way up here, okay? You should actually be kind of surprised by that at first glance. It should look a little bit weird. It's either coupled much more strongly to the standard model than you had expected, or it has an energy density that's much higher than you expected. And so something should, some alarm bell should be going off in your head. Of course, it could be a photophilic axion. It could be, there are various other kinds of production mechanisms it could be, some of which are very tuned. For example, if you just wanted to do this with misalignment, you can see that even pushing up here, you start needing like 10 to the -3 tuning away from pi. However, another thing is just completely untuned axions, a pair of them, one of which was down here, one of which was up here, and this guy donated all of his energy density to the guy up there. So with that, I'll conclude. I hope this is exciting. You can talk to me afterwards about what happens with taking into account perturbations properly. It really just goes in the direction of equalizing things, although you also end up getting a very large enhanced substructure on small scales. So that can be really interesting for certain kinds of either gravitational indirect detection of dark matter, things like this. But yeah, talk to me afterwards. Send me an email. Of course, the conference is nearly over, so I don't get to show you all of the pretty movies and stuff that I'd like to. Well, I can let the movie play while you guys ask questions. This is a movie of this actually happening, the substructure forming. So you'll see that as it oscillates, this might look a lot to you like preheating, for example, because the dynamics are somewhat similar. You got the formation of some clump structures which decay because they're not stable over long periods of time. But the residual fluctuations do collapse into gravitationally bound structures later. So with that, I'll conclude. Thank you for your time. I hope I've convinced you that friendly axions can be pretty interesting for some of your direct detection experiments, and that it may be one of the few avenues that we might have to thinking about something like string theory. If I see one axion in my theory, I'm not a string convert. But if I start seeing 2, 3, 4, 5 that are coupled together in some way that might be reminiscent of UV physics, That might be one of the very few. That might be one of the very few avenues we have to getting any hint about what physics looks like way up at the Planck scales. So, thank you.
Hi, it's a really nice talk. Can you perhaps quantify a bit more the statement about the fact you still get this boost, even if it's a subdominant, the friendly pair is a subdominant contribution? Because if I imagine like an Axiverse scenario and I have this like, distribution of masses over, many orders of magnitude, it could be really subdominant. So do you have some more?
So this is a point that, like, it took us a little bit to recognize. I feel like this point has not permeated the community as much as it should have, although I'm sure many of you guys understand this very well. I have a little cartoon here. I tried to draw this. Okay, this is a dumb cartoon, so you're going to have to bear with me. But on the x-axis, I have something like mass, which many orders of magnitude. This is clearly a qualitative picture. On the y-axis, I have something like this 1 over f. Okay. If I just think that every axion here is picking up some kind of naive order 1 misalignment, then all of these guys, this region might be very populated. There, of course, is some region way down here where they would have picked up too much energy density, have overclosed the universe, so we have an observational limit that nothing can sit down there. But all of the guys that are sitting up here, they actually, when you look at that figure of merit, which is something more like 1 over f squared times the energy density, they collapse onto a line. And then when you imagine sampling a distribution, that expands to a band, right? Because you might say, oh, if there's 100 axions, some of them might have order pi over 10 tuning, some of them might have 9/10 pi, whatever. So the point is, the first axion you're likely to see in your experiment is not necessarily the dark matter axion, if an axion is even dark matter at all. The first axion you're likely to see in your experiment is the one that happens to be sitting in your mass range. Okay? And the point is that you may be concerned that, oh, this friendliness, like there's some chance involved, I don't know, but the chance, it doesn't have to be that I got lucky and that my dark matter axion had a friend. It's just any axion had a friend, and that axion was one that I could do some sort of haloscope type experiment for. Yeah. I hope that, clarifies that.
Yeah. One other question, maybe?
Yeah, hi. Sorry, yeah, thanks, Chet. Good talk. Oh, yeah, here. Okay, I have a lot of questions, but I have to keep it to one, apparently. Let's see. I guess about structure formation. Could you go a little bit more in detail then, since you had to be quick on it? I'm guessing, just for some intuition, that it's when you have on small scales, maybe higher densities, that you can get these sort of conversions. But then why does it decay, for example? And then what kind of, I don't know, what kind of typical scales should you think about?
So, I'll say very short words about structure formation. To tell the story properly would take more time than I think a polite man would give me. The simple statement is just this. By nature of being in autoresonance, we know that the axion must be exploring a relatively large field value, angular field value of its parameter space, because it had to be in order to adjust its frequency. If you're probing a large value of, or a large field value of your parameter space, a large field value, that means that self-interactions are playing an important role. And then if you just think about what this potential looks like, it is less than quadratic, which means it's experiencing attractive self-interactions. And if you work this out carefully, you'll find it's a parametric resonance instability. This is very similar. The physics here is virtually identical to the physics at play in these so-called large misalignment scenarios, which me and a couple of other people worked out a few years ago, I think some of which might be in the audience tonight or today. So you just get a parametric resonance instability that grows a lot of structure. However, the thing that you should think of is just that at late times you have essentially an enhancement to what looks like the primordial power spectrum at some scales. The scales are given by the scales that are entering the horizon at the same time the axion mass is entering the horizon.
Okay, and it's always going to be temporary, I guess.
No, it's not going to be temporary. Just those clumps that you saw in the movie are temporary, because those are guys that are bound by self-interactions. The things that are not going to be temporary are the guys that are bound by gravity later. Yeah.
Okay, one absolutely last question.
Actually, I had a very similar question, but since you mentioned the movie, did you this movie corresponds to an expanding background or just flat? Okay.
Yeah. That paper is out today, so there's way more details in that paper than I can say in just these seconds. But yes, that's an expanding background. Simulations those were run by this guy at University of Washington, Zach Weiner, who's a far better computational physicist than I am in terms of making things go on the computer. So, yeah.